So we haven't talked much about extremes, so I decided to add under impacts one on land heat wave extremes, and I will have one on marine heat waves, ocean extremes. Intuitively, you all know what extremes mean in real life or even in climate. Heat waves, floods, even droughts, which you typically tend to think of as slow growing things. Now there are so-called flash droughts as well. So these are, and of course there are cyclones and storm surges, inundation, etc. So we will touch on just heat waves to get a sense of how we think about extremes, how we think about global warming impact on extremes, and what it translates to. What I'm getting some message about the restarting the machine, so I'll wait. So here we are looking at just a typical temperature distribution in the range here. Let's say this is the 20th century distribution observed in some location in Zagreb, which doesn't even matter. So you have the warmest temperatures and the long-term seasonal distribution with the probabilities of occurrence of these temperatures shown here. And what global warming typically does, let's say here it is projected for year 2040 for Zagreb, it shifts the distribution towards warmer mean temperature. Here the peak temperature probability is not shown to change, so the distribution has just shifted towards a warmer mean, and the mean has not really increased here because the peaks are at the same level. So you end up with, in the new climate, you end up with a lot more hot days with these probabilities, and you get some very hot days with a lower probability, but they have increased compared to the previous distribution in the 20th century in terms of the warm anomalies on top of the mean. And then you have some that are referred to here as wicked hot days, which are expected to come occur at 2040. The probability is low, but it's still there. So these are the way things change. Of course, you can also look at it this way, where you are looking at again temperature, and you are looking at a threshold. When you cross the threshold, you call them heat spikes, and when they last for a certain time, like greater than 5 days, then you call them heat waves. Okay, then there is the idea of exposure, which we'll come to. So here is the start date, and this is the end date. So obviously it has a duration that exceeds the definition of WHO, where heat waves are defined as greater than 5 days. But you can see that it is relative to the background temperature. So a person in a cold country may consider a heat wave which is exceeding their expected temperature by a certain threshold, but the same temperature in a warm country may not be a heat wave at all. So it's relative to where you are. That's another thing to remember. So you have a climatological mean, there's a threshold for defining heat wave, and then you have also similar things for marine heat waves and spike. So this is actually from the marine heat waves. And the thing to remember is on land atmosphere, air has very low heat capacity, can warm up very rapidly, can move very fast, and can cool down very rapidly as well. Whereas in the ocean, everything is 1,000 times slower. Density is 1,000 times higher, but you end up with warming up that is slower, cooling down that is slower, and the duration, etc., can be similar because it depends on the process. And the ecosystem impacts can be similar, or ecological impacts on marine species can be similar as on land, because they are used to certain rate of change of temperatures in the ocean, and when it exceeds that temperature and changes rapidly relative to what they are used to, then it is still a heat wave. So this is from a nice paper by Nikki Gruber that just came out, a great scientist and a really nice person who does very careful and good science. So here are the metrics associated with an extreme event. Here he's talking about compound events, which we will look at. The metrics included were the intensity, magnitude, duration, heterogeneity, abruptness, and recurrence. So they have added more details to how to consider. So when you talk about any particular climate variable, whether it's rain, temperature, or whatever, you are talking about how abruptly it changes, how it goes above the threshold relative to the climatology. So you can think about the magnitude, and you have intensity. So this one is much more intense above the threshold compared to this one. Heterogeneity is basically the range over which these events can happen within one event that has crossed the threshold for meeting the definition of a heat wave, for example, or any kind of extreme. So within the duration you have this range of intensities, and then the recurrence interval, which is happening over certain periods. So we said before that climate change loads the dice, which means the recurrence interval, which could be let's say once in 50 years in the natural climate, or in the 20th century before human impacts became significant, then climate change, as warming continues, will make that event much more likely. Will change the recurrence interval from 1 in 50 years to maybe once in 20 or once in 10 or whatever, depending on what particular climate variable you are thinking about. So you can do all these kinds of details, and you can of course also look at the likelihood that the mean temperature, for example, or any mean climate variable doesn't just shift, but its mean also changes. So here the distribution has shifted, again giving us extremes and far extremes here. So shifting relative to a threshold here, and present day world with anthropogenic forcing is what we are looking at, the envelope. And in this case you are of course shifting the cold extremes as well, which you have to keep in mind. Okay, so the heat waves can be riding on a higher mean temperature, which means that essentially we have to also worry about the shift in the climatology itself, because mean temperatures go up, everything happens in a warmer world, and there are many more details associated with that. Once you have all these things together, then you can go back and look at the ratio of extremes. What would have happened if there was no anthropogenic effect, no increase in greenhouse gas, no anthropogenic warming? Then the likelihood of extremes would change, has changed in fact. So you can see that the ratio of extremes over time has increased, and this is the mean envelope, and these are things that are jumping out of the trend itself in terms of the range of ratios, standard deviations, or quartiles, quantiles, 5th percent to 95th percent, and so on. So there is many statistical ways to do it, but schematically speaking, anthropogenic forcing is increasing the likelihood of extremes, whatever the climate variable you take, precipitation, temperature, and heat waves, and so on, that cascade from that. So how do we say that this is happening? Basically it goes back to what we said before in terms of attribution science. So this is an example. Researchers have published more than 170 studies examining the role of human-induced climate change in 190 extreme weather events. So these are the color codes: more severe or more likely to occur, less severe or less likely to occur, no discernible human influence, and insufficient data to make a clear attribution to human contribution. So heat waves clearly have they have looked at number of extreme weather events which is in the range of 50 or more, and attribution says that the human impact has caused more severe and also driving more occurrences, which means the recurrence period has been reduced. Droughts have a significant contribution as well. Rain and flooding have a significant contribution, even though there are many events where there was either no discernible event or the data was not insufficient and the conclusions could not be drawn. This doesn't mean that the numbers are not higher. It just means that going into the future, we need to track these things much better so that in 10 years, 20 years, we are able to improve the attribution of these extreme events. Oceans, we will look at a little bit more detail in the next podcast. Cold ice and snow and storms. So here you can see that because of data and there are also places where events are less likely or going to be less severe because global warming tends to expand the tropics, warmer temperatures, shifting baseline of the colder temperatures, as we saw from the shift towards warmer temperatures. For example, here the numbers are dropped in this range once you shift the distribution. Okay, so those are the kind of things to remember. And quickly to run through some heat waves, this is how things are done: a heat wave index and description, heat wave count, so count of distinct heat waves during a year per grid cell. So you take the globe or a place and you look at the data in grids where data is sufficient to draw conclusions. Typically you would want to do it at as fine a resolution as possible, because the vulnerability to heat waves and other extremes can be very small scale. Neighborhoods within a city can be very differently vulnerable to a heat wave because of access to heat care, air conditioning, public transportation, hospitals and other things, water, etc. Heat wave days are the number of days of heat waves per year per grid cell, which measures the trend in total duration of heat waves. Heat wave degree days, which comes from the energy sector as well. Sum of degree days of heat wave per year per grid cell, which captures both the change in the duration and change in the intensity of the heat waves, as we saw in the previous plot. Okay, heat wave mean length in days of individual heat waves per year per grid cell, which measures the trend in duration per heat wave. So you have always look at intensity, duration and frequency. If the duration of heat waves are increasing and intensity is increasing and frequency is increasing, you are going to magnify your vulnerability greatly. So adaptation measures have to take quick action, urgent action. Heat wave mean degrees over threshold, mean degree C above the heat wave threshold per year per grid cell, measuring the trends in heat wave intensity. Okay, so these are the kinds of things, and that's the I went in the wrong direction. So what happens with these extremes is also we have to consider who is being exposed to these. So change in percentage of population greater than 65 from 1980 to 2018 shows that other than Africa, much of the globe has seen an aging population, which means even if the heat waves didn't change, the exposure and disease outcome, morbidities and mortalities would be higher because you have more vulnerable population. And then on top you are adding heat wave degree days, number of heat wave days, change in mean length and change in heat wave degrees over the threshold, so the intensity. So when you look at each one of them, you can see that there are upward trends in the global mean for all of these. But when you consider the age group and the increased vulnerable population, then you can see that the exposure weighted mean changes in each of these quantities is alarming, much worse. So except for here in the change in heat wave mean length, that doesn't seem to show much of exposure change, age group dependence, and the same here in change in heat wave degrees over the threshold. Nonetheless, change in heat wave degree days and change in number of heat wave days does affect the exposure of the vulnerable population. So this is an introduction to the extremes done briefly in this course, which is an introductory level, so the book keeps it fairly simple, doesn't get into the details of the extremes, but I've kept these as 8A, 8B, 8C because 8 is the podcast that is the main, chapter 8 is the main one, sorry, not 8A, 8B, 8C. Chapter 8 is the main content is put up front, and I have added these at the end so you can follow up if you are interested in such details. And of course I have a full course on monsoon extremes which goes into lots of dynamics and predictions and other details of the rainfall extremes. Okay, so here it is done at an introductory level, as you can understand. Okay,